Now let's talk about um, fan in and fan out. So these are limitations that, or these are things that limit how big our gates can get and how many gates they can tie to. So first, let's talk about fan in. So fan in describes the what limits the amount of inputs we can have on a gate. So let's think about a CMOS NAND gate, and let's think about a big one, right? So what's going to happen is we're going to have a transistor, transistor, transistor. Oof, going a little cattywampus here. So we're going to have oops, a transistor, another transistor, another transistor, another transistor, and let's just do one more transistor. And also that means that we're going to have all of these guys, we're going to have a bunch of transistors up here. I know this isn't the most gorgeous transistor drawing, so I got 1, 2, 3, 4, 5, so we need one more. So this is very, very kind of rudimentary drawing, but at this point you should kind of be able to visualize that these are PMOS transistors and these are NMOS transistors. Um, Now, if we are in a scenario where plus is conducting to the output, right? If plus is connecting to the output, it doesn't matter what transistor uh, the plus reference is going through. It's it's always has to just go through one transistor, and so that's not a super big deal. But and though we say that these transistors don't have a resistance to them, they do. There is a voltage drop across each one of these transistors, meaning that if so this is actually not perfect because of the because we're going with zero. Uh, but the strength of this reference for zero kind of declines with each transistor. So if we were to say the strength of the zero here, at this point it might be on a scale of 1 to 10, might be a 10, and then 9, 8, 7, and then this is a 6 here. So we're just kind of using vague terms here, but it's the pulling power of that zero. And so as it hops through all these transistors, its strength kind of decreases a little bit. And the more transistors, the less strong that zero is. And so that is what fan in is, right? So each one of these transistors represents an input, right? So we've got A, B, C, D, and E. This is a 5 input transistor. So it's a it's a physical limitation that we deal with. And for most gates, I think it's around like 7 that it starts to become a real problem. And so that's just something that you have to work around. If you want to do any bigger gates, what you'd have to do, so this is an AND gate, is you would just have to take an AND gate and cascade it into another AND gate. Um, so that's fan in. Now let's think about fan out. Fan out describes how many outputs a gate or how many gates a gate output can connect to, meaning this is going to connect to multiple gates on the output. And what affects that, or why is that important? Well, consider this. We've got let's do an NMOS transistor here. We've got an NMOS transistor, and let's just make an inverter, I guess. So we've got an NMOS transistor, and so we're going to say that we've got a 1 here, and this is a NOT gate. And now let's say that this is going into the input of multiple more gates, right? It's going to multiple gates. So what that means is that this is hooking to, if it's a CMOS device, for each gate, it's at least hooking to 2 transistors. So hook into a transistor here. So that's 1 gate, 2 gates, and it's hooking to another gate. So these could be ands, ors, nands, nors, whatever. It doesn't really matter. So remember that each one of these transistors has a capacitor kind of built into it, right? Its gate is a capacitor. And the more capacitors that we add on here, it's like having multiple buckets that are getting tied together. And the more that we have tied together, the harder it is for this single transistor to fill the rest of these buckets, right? Just kind of think of these transistors as buckets right now. And so that becomes a physical limitation where you can only fill up so many buckets before you really start to run into problems here. And so that problem, or that number for CMOS gates is, let me see here, I've got it written down. It's about 20, right? So we can go to about 20 gates, which is pretty big, but it's still something to consider, right? You might have, say this is a signal A, and we've got A referenced all over the place. So that's when you might want to start consider adding in buffers. Buffers can kind of help alleviate this problem, but it still is going to have a propagation delay component to it, right? So the more we have hooked onto here, the more capacitors we have, and the longer it takes to charge. And so once again, that's going to affect our rise time and fall time. Both of these factors affect our, I'll write those terms down actually. Rise time, oops, that's a fun looking R. Rise time and fall time. So when I say rise time and fall time, what that means is how long it takes for the signal to rise, and fall is how long it takes for the signal to fall. And usually they're pretty closely related. They're going to be about the same rate. So modern values for this amount of time, it's around 5 to 6 nanoseconds. So that's a constraint that we have to deal with, and that's assuming that we're following our fan in and fan out requirements for our gates. So these are usually things that might be linked to our data sheet or something that we might be able to compute, but they are real physical issues that we have to deal with.